Welcome to your podcast for Lesson 44, Problem Solving with Tension. After viewing the podcast, you should be able to practice more complicated tension systems and tension problems. We really already know how to do these problems. It's just that instead of actually calling it a tension, we've called it an applied force. So it's just taking what we've learned in the last few lessons and applying it to the same types of problems that we've been doing. Okay, if you take a look at number 1, we're solving for the tension in the string. Now we know that this 1 kilogram mass is going to have the downward force of gravity acting on it. And remember that Fw is equal to mg, so 1 kilogram times 10 is going to give us an Fw of 10 newtons. We also know that tension, which is acting in that upward direction up the string, because this object is at rest, we know that F net has to be 0. The only way for F net to be 0 is if the tension is equal to 10 newtons as well. We're going to assume that this bottom system is at rest as well. And now we have a 4 kilogram block hanging, which again is going to have an Fw, but this time 4 times 10 is going to give us that 40 newtons of force. And this time I have 1, 2, 3, 4 different support ropes. So I have to take that 40 newtons and divide it by 4. So the tension in each of those ropes then is going to be 10 newtons. Okay. Now, if it's at rest, that means my F net, again, has to be 0. And so that means that that applied force that's acting to hold that system in place at rest has to be equal to the tension in the ropes. So Fa is equal to 10 newtons as well. Okay, in this system we have a 2 kilogram block sitting on top of an 8 kilogram block. And I know if I were to just look at the forces on block number 1, it's going to have an Fw, so I'll call it Fw1, caused by gravity. And that contact that it's making with box 2 is going to cause it to have a normal force, which we'll call Fn1. Now we know that those two are going to be equal and opposite to each other, and since it's a 2 kilogram block, they would each be equal to 20 newtons. Okay. When I look at block number 2, okay, I know that it's going to have an Fw that acts straight down, again, the box's weight, and if it's an 8 kilogram box, then 8 times 10 is going to give you 80 newtons for its weight. But now, when I consider its Fn, which I'll just kind of draw over here a little bit, I know that I not only have to consider that weight of box 2, but I also have to consider the weight of box 1 because it's sitting on top of it, pressing down on it. And so to determine that normal force on box 2, I have to take the 20 newtons from box 1 plus the 80 newtons from the weight of block 2 to give me a total Fn of 100 newtons on box 2. And so we can answer questions 4 and 5 by looking at our diagram here. What is the force of block 1 on 2? Well, its weight is pushing downwards, right? And we labeled it Fw1, which we know is 20 newtons. And we know if block 1 acts on block 2 with 20 newtons, we know that block 2 acts upward on block 1 with 20 newtons. Okay? And that time I would be referring to the force pairs that are labeled in yellow. Okay, in this system, we know that the only external force acting on the system is this applied force of 28 newtons. And so that tells me that that's my F net on the system. Now, that F net is going to be what causes this system to accelerate. And so I know I can solve for my acceleration of the system by taking that F net and dividing it by the total mass of the system. So in this case, 28 newtons. Okay, divided by my total mass of my 3 blocks, so 8 plus 2 plus 4 gives me 14 kilograms. Okay. That's going to leave me with an acceleration of 2 meters per second squared. Okay. Next thing I have to do is find my net force acting on each individual object. And for all 3 boxes, I'm going to use that same equation of F net equals mass times acceleration. So for block number 1, 8 times 2 is going to give me a net force of 16 newtons. On block 2, 2 times 2 is going to give me an F net of 4 newtons. And on block 3, 4 times 2 is going to give me an F net of 8 newtons. Okay. Now let's think about those internal forces that are acting on this system. So I go back to block number 1. I know that I've got 28 newtons coming from the outside, and I know that block 2 is going to push back on that system. Okay. Block 1 is then going to push on block 2. And so I know I need to end up with an F net of 16 newtons. The only thing that could go in that spot right there would be 28 minus 16, or 12. So I know that has to be 12 newtons. Now that is an internal force pair, so I know that this has to be 12 newtons as well. Okay. Now when I look at block number 2, I know block 2 is being pushed on by block number 1, but block 3 is pushing back. So if you look at the internal force pair, right, from our first one, we know that's 12 newtons. So the only thing that I can put in that blank to equal 4 is 12 minus 4 is going to give me 8. So this has to be 8 newtons. Okay. Now we know that as block 3 pushes back on block 2, block 2 is going to push on block 3 with that same force, so that's 8 newtons as well. So when we look at our questions down here, what is the force 2 on block 3? So that force of block 2 on block 3, we can see right here. Okay, and we know that that is 8 newtons. Okay, and then question number 9, what is the force of block 1 on block 2, which would be this yellow arrow right here, and we know that that is 12 newtons. Okay, on this system we have a block that has a mass of 1 kilogram that's accelerating downward at a rate of 1 meter per second squared. Okay, so acceleration is 1 meters per second squared, and it's going downward. Now, what that tells me is that the FW, okay, has to be bigger than the tension if this is moving downward. Okay, so make yourself a little note of that. Okay, if it's moving downward, then FW has to be bigger than the tension. Our FW we can solve for. We know FW is equal to mg, or in this case 1 times 10, which is 10 newtons. And I know that I can now write net force equations for this. Okay. Newton's second law tells me that F net is equal to ma, and for this block I know it's a 1 kilogram block accelerating at 1 meter per second squared, so that's going to leave me with an F net of 1 newton. Okay. To find the tension, I know I can say that F net is equal to my FW, because again we've determined that that's going to be the bigger of the two forces, minus the tension, and when I rearrange this I can say tension is equal to FW minus F net. Okay. Or in other words, 10 newtons minus 1 newton for a tension of 9 newtons. Okay. You could also set mass times acceleration equal to Fw minus t and rearrange and solve for that. It just depends upon what series of questions you're being asked to answer for a particular problem. Okay, now in this system we have our 3 blocks being held together by a series of ropes or cords, and we're going to treat this problem the exact same way we did when the boxes were touching each other. I look at this system, it doesn't say anything about friction, so I know the only external force acting on that system is the applied force of 18 newtons to the right. And so I know that that's also equal to my F net of the system. Okay. I still go about finding my acceleration the exact same way. Okay, A equals F net over the mass of the whole system, or 18 newtons divided by 6 plus 4 plus 2, which is going to give me 12 kilograms. Okay. And so when I plug and chug this, 18 divided by 12 is going to give me 1.5 meters per second squared. Okay. So my acceleration is 1.5 meters per second squared. Okay. Now, again, remember your next step is the net force acting on each individual object, and I find that by using F net is m times A. So 6 times 1.5 for the 6 kilogram block is going to give me an F net of 9 newtons. If I look at the 4 kilogram block, 4 times 1.5 is going to give me an F net of 6 newtons. And the 2 kilogram block, 2 times 1.5 is going to give me an F net of 3 newtons. Okay, so I'm going to come over here to my 2 kilogram block, and I know I've got an 18 newton force acting to the right, which I know is going to cause a tension in this string. And to solve for that tension, I just look, I've got two forces going in opposite directions, the applied force and the tension, and I need to end up, remember, with an F net of 3. Okay. So 18 minus 3 is going to give me 15 newtons. So that 15 newtons for tension 2, okay, is acting in both directions on that string. Okay. Now, we also know then that we have this 4 kilogram block, which is going to be causing a force of tension in the string as it moves. And we know then I need to, on this 4 kilogram block, end up with 6 newtons for our F net. And so the only way that I can get that is if I take that 15 newton pull, okay, again going in that direction, and subtract from that some number going in this direction, right, to end up with 6. Okay, so I can rearrange that 15 minus 6 is going to leave me with 9 newtons. Okay. Now that 9 newtons of force, okay, we know is also going to be pulling back on the rope towards the right as that system pulls on that 6 kilogram block. And if you look, we said we should get that 9 newton force acting on that 6 kilogram block. Okay, you've already done this problem before, you just didn't realize it. But if you think back to the last exam review, you had a problem where a sled was being pulled by a rope at an angle. You called it an applied force, but really it was a tension. And so the first thing to do, just like we did before, was to take that applied force, or the tension, and split it into its x and y components. So I'm going to call that Tx, and I'm going to call the vertical component of it Ty. Now, I know that I've got an acceleration of 2 meters per second squared, right? And that acceleration is going to be in that direction. Again, remember, what causes an acceleration is a net force. And so what that tells me is that Tx, or that horizontal component of the tension in the rope, is going to be what causes this 10 kilogram object to accelerate. So I know that Tx is equal to F net. And I can solve for F net by taking the mass times the acceleration. So in this case, 10 kilograms times 2 meters per second squared is going to give me an F net of 20 newtons. And so there's the first part of our problem. Okay. Second part, finding the tension. Well, I know that if this is my angle, and I've created my little right triangle using my parallelogram rule, the tension is the hypotenuse because it's directly across from that right angle, and my Tx, or that 20 newton side, is adjacent to the 30-degree angle. So I can solve for tension using SOHCAHTOA. So adjacent and hypotenuse, I'm going to use cosine. Okay? So the cosine of 30 is equal to my adjacent over my hypotenuse. So when I rearrange, I get tension is equal to, I'll plug in that 20 newtons divided by the cosine of 30. And when you plug and chug this, you end up getting 23.1 newtons. Okay. So we've got 23.1 newtons of tension in that rope. Okay. Now, I know that this 10 kilogram block is going to have an FW, right, that goes straight down, okay, because gravity acts towards the center of the earth. And I know that FW is equal to mg, so a 10 kilogram mass times our value of g, 10, is going to give me an FW of 100 newtons. Now, we know that the normal force is going to act perpendicular to the contact surface, okay, but it's not equal in magnitude to our FW, because don't forget, we have a part of our tension force that's acting in that upwards direction as well. And so if you look, I've got Fn and Ty pointing up and Fw pointing down. So when I find Fn, I'm going to need to set the Fw equal to the normal force plus that Ty, or that vertical portion of tension. And you've experienced this, you know, if you've ever pulled a sled across the field, you know that as you pull on that cord at an angle, the front end of that sled lifts up a little bit. And so there is a little bit of that weight component that is sort of being counteracted by that upward pull on the string. Okay, so we have to solve for our Ty so that when we rearrange this equation, Fn is going to be equal to Fw minus Ty. I can get my answer for Fn. Okay, so if we go back to our right triangle, Ty is going to be equal to this side over here, which is opposite of that 30-degree angle. So I know I can say that the sine of 30 is equal to that opposite, Ty, divided by my hypotenuse t, which we've just solved to be 23.1. So when I rearrange this then, okay, I'm going to end up taking Ty is t, 23.1 newtons, okay, times the sine of 30. Okay. Sine of 30 is 1/2, so 23.1 times 1/2 is going to give me 11.55 newtons. Okay. Now, I can plug this in down here. So I take my 100 newtons for Fw and subtract my Ty, 11.55 newtons, and that is going to give me an Fn of 88.45. Okay, this is an Atwood's machine, which is simply just a pulley with a rope over it and two different masses hanging on it. Now we know that each of these masses is going to have an Fw which acts straight down, and I still am going to calculate Fw the same way. So we'll just call it Fw1 and Fw2. And I know that Fw is equal to m times g, so 4 times 10 is going to give me 40 newtons on this first one, and 6 times 10 is going to give me 60 newtons of Fw on the second one. Okay. Now we know what's going to happen. That 60 newtons is pulling a little bit harder, and so it's going to cause this system to kind of move in that direction. And so that tells me two different things here. The acceleration is in that direction, and that is also going to tell me some things about tension that we'll see on the next screen. Right now, though, I know my acceleration is going to be in that direction, and again, what causes an acceleration is a net force, okay? And so I can write two different equations for this net force. We know F net is equal to m times a, but I don't know the acceleration yet. But I do know I've got two forces going in opposite directions. I've got this 60 Newton force and this 40 Newton force, and so I can just subtract them to find my overall F net on the system, which 60 minus 40 is going to give me 20 newtons. I can use that F net of 20 newtons then to find my acceleration, because we know that F net over my total mass of the system will give me my acceleration. And so we've just said my F net is 20. And the total mass of this system is going to be the masses of the two blocks. So 4 plus 6 is going to give me 10 kilograms. Okay, so 20 divided by 10 is an acceleration of 2 meters per second squared. Okay, our next step is to find the F net, or the net force acting on each individual object. So just like we did on all our other ones, we know that F net is equal to mass times acceleration. And so for the 4 kilogram block, right, we know we have 4 kilograms times our acceleration of 2 meters per second, which is going to give me an F net of 8 newtons. For the 6 kilogram block, same thing. F net is equal to m times a, so 6 times 2 is going to give us an F net of 12 newtons. Now we can find the tension of the system by analyzing the forces that are acting on only one object of the system at a time. So let's just, for example, take the 4 kilogram block. We know that it's got an FW, which is acting straight down, and we know that that FW is equal to 40 newtons, m times g, or 4 times 10. And I know that overall, to get this F net of 8 newtons, there's a tension acting upwards, okay, in that rope. Now, I know that this system, remember, is going to go up around the pulley this way because that 6 kilogram mass is causing that net force in that direction. So because this 4 kilogram block is going to be moving up, that tells me that tension has to be bigger in this case for that 4 kilogram block than its FW. So that's going to allow me to write an F net for this particular equation, or for this particular situation here, that says the F net on this block, okay, is going to be equal to tension minus FW. I can rearrange this and solve for the tension by saying F net 1 plus FW. Okay. Or an F net of 8 newtons plus an FW of 40 newtons, right, is going to give me a tension of 48 newtons. Now I should see that same thing for my tension when I solve over here, because again it's that same rope within that system, so it's going to have tension acting equally on it. So again, think about the forces that are acting on this particular block. We know we've got its FW, which is acting straight down, so 6 times 10, m times g, we said would give us an FW of 60 newtons, and again that tension is going to be acting upwards in that string. Okay, but now we know that this part of the system, that 6 kilograms, is moving downward. So what that tells me is that my FW2 has to be bigger than my tension. So for this particular one, when I write my F net, okay, I know that my FW2 is my bigger force, so I take that minus tension. I can then rearrange this to solve for tension to FW2 minus F net of 2. Now remember, we've said the F net on this block should be 12 newtons, so for my tension, I have 60 newtons minus 12 newtons, and that's going to give me, again, a tension of 48 newtons. Okay, 48 newtons. Sometimes you will see this equation, although you don't have to use this, but for an Atwood machine, if you're not given anything else other than the masses, you can calculate the tension by setting it equal to 2g times the quantity of mass 1 times mass 2 divided by the quantity of m1 plus m2. But you don't have to do that for these problems. You'll always be given enough information that you can figure out the F nets on each object and then therefore solve for the tension in the rope of that system. Okay, Okay, when you look at this system, you've got a 2 kilogram mass that's hanging over the edge of the table with a rope running over that pulley. And so we know that that's going to have an FW as gravity acts on it, and FW is m times g, or 2 times 10, which is 20 newtons. The problem doesn't say anything about friction, so we're going to assume that that's the only external force acting on this system, so that's also going to be equal to the F net of the system. I can solve for my acceleration then, because I know that acceleration is equal to F net divided by the total mass of that system, or in this case 20 newtons, divided by the 10 kilograms plus 2 to give me 12 kilograms on the bottom. And when you plug that in your calculator, 20 divided by 12 is going to give you 1.67 meters per second squared for your acceleration. Okay. Now, I know that the F net then can be calculated for this box by taking its mass times the acceleration. So a 2 kilogram mass times 1.67 is going to give me an F net of 3.34 newtons acting just on this 2 kilogram box right here. As gravity pulls this 2 kilogram box downward, and therefore the 10 kilogram box is going to slide this way, it's going to create a tension in that rope. And since the 2 kilogram box is going to be moving downward, that tells me that that FW has to be bigger than the tension. So I can write another equation for the F net on that box that says that FW minus tension is equal to the F net. I can solve for tension then, like I'm asked to do, by rearranging this equation. Tension is equal to F net, or I'm sorry, FW minus F net. Okay. And so my FW was 20 newtons minus the F net for that particular box, which we said is 3.34 newtons, and that is going to give you 16.66 newtons for your tension.